So I'll kick it off anyway. Hi folks, welcome to BSides. My name is Niall McGrath and I'd like to talk to you today about how digital forensics fits into the world of forensic science. And we'll also talk a bit about cloud forensics as well in the context of AWS. This is the agenda we'll talk through today. I'll just introduce myself. I'll give a background on forensic science, give an overview of digital forensics in the context of two research papers I wrote in relation to investigating file encrypted contents on NTFS and OSX. We'll talk a bit about DFIR in AWS, and we'll wrap it up then for questions, if that's okay. So currently I'm the SOC manager, Security Operations Center manager in Workday. I'm there for about 3 years, just a bit over 3 years. Previous to that, I was in Amazon incident response, working as incident response and the focus on digital forensics. And previous to that, I worked in Bank of Ireland for a few years, had a number of roles there, developer, programmer, technical designer, architect, and finished up with IT security, and again with a focus on digital forensics. And while I was there, I completed my PhD in University College Dublin, and that was in digital forensics as well. So you can see that theme of forensics developing there. Previous to that, I was in ICL as a software engineer, and then I worked in Japan as a mechanical engineer. That was my primary degree in mechanical engineering from University of Limerick, and I worked as an architect there as well. Met my wife there, and this is the gang. That's Mazio, Yana, Jude, and Leon. So let's talk about forensic science, forensics as it's abbreviated to. Forensic science is, it's a domain of sciences, and it's composed of the chemistries, the physics, the geologies, the biologies. And incidentally, geology is the study of the Earth's structure, the Earth's structures and how they interact with each other under various conditions, right? So we have this domain of sciences, right? So why are we using this domain of science? I'll tell you, it's to answer a question or a series of questions in a court of law, criminal or civil law. And the mechanism through which we do this is through evidence, admissible evidence. And depending where you are, what jurisdiction you're in, admissibility can be many things, many criteria, etc. But one thing it is, or the many things that it is, it includes relevance, completeness of your evidence, reliability of your evidence, authenticity of your evidence, and indeed repeatability. If you've got a methodology that generates evidence, it has to be repeatable no matter what location. Belfast, Dublin, London, Hong Kong, Tokyo, it has to be repeatable to yield the same results, and equally so the same error rates as well. That's just as critical. So, to get the admissible evidence, we have forensic services. And here's a list of forensic services. I'm going to scoot through them really quickly. But these are services that help us get admissible evidence into court. We've pathology, and this underlines medicine and science, and it completely underpins the patient's life care, from start to finish. And there's a mechanism there called the autopsy, the post-mortem. And this is really important for determining cause or reason of death, organ failure, etc. We've also got anthropology, and this is where it gets a bit macabre now, so bear with me. Anthropology is the study and detection of skeletal remains, and from there then the detection to see, or being able to distinguish if they're animal or human, ethnicity, gender, etc. And entomology, this is the study of insects and the study of the growth phases that they go through, because that will bring a lot of really rich forensic information to a crime scene in terms of chronology and timelines, etc. Psychiatry, it's all about human behavior, and in particular abnormality in human behavior and profiling those abnormalities. Engineering would be used by the insurance companies predominantly to determine if a claim was falsified or to prove if it's legitimate, equally so. Odontology is the study of dentition, the uniqueness of dentition or teeth. Ballistic science is, the study of rectilinear motion in conjunction with firearms, etc. Determining the trajectory of a bullet. You can determine distance, etc. Ballistics can also be used to determine if something or an object or somebody was pushed from a ledge or indeed jumped from a ledge. Toxicology is the study of poisons and how it interacts with the human body, etc. And toxicology reports would be a very important evidence artifact in a court of law. So this is the executive summary that I'm going to describe in relation to the two papers, right? And it's, imagine you're a digital investigator, right? And you come across file encrypted material, right? The problems that you face are obviously, trying to extract evidential value from your file encrypted contents. So, I mean, you just assume that you don't have the keys to decrypt, right? You're not going to brute force. Maybe the tools aren't reliable and the tools themselves aren't admissible in court. And you're not going to use cryptanalysis techniques to defeat the decryption, right? So how are you going to do this? How are you going to extract your evidential value? And the typical scenario where you could use encryption, and the talks are going on right now as well, is the widespread, malicious and nefarious use of encryption would be the widespread distribution of malware, for example, and indeed in conjunction with steganography as well. Also in the widespread dissemination of illegal material like terrorist-related information as well. So these are kind of typically the nefarious situations and cases that are being investigated. So, I mean, what the research was proposing was to locate the plaintext file name, because it can be transformed in that encryption process. And then from that then, identifying the plaintext contents of that file. And how we went about it was we characterized the file encryption process as a series of input-output operations, So then we could track those system events in the journal files of the systems we were looking at, which happened to be NTFS and OSX. Okay. So let's look at NTFS and $log file, right? And the $log file is the journal file in NTFS, right? And, so what is a journal file? Why do we use a journal file? Essentially, a journal file is there to restore the system on the event of a sudden outage or a disk failure, for example. And it's there to restore the system to its former integrity, right? And how does it go about that? What does it store in the journal file? Well, it stores metadata on the file system, recording the change in the file system. For example, the new files that were added, the files that were deleted, that were modified, truncated, etc., renamed. So it contains metadata information on metadata. And there's two types of transactions in the NTFS $log file. And it's the redo and the undo. And these are specifically for that scenario. For example, the redo is, the transaction gets cached in the journal file before it gets written to the actual disk. But before it gets written to disk, imagine if you had that failure, that system failure that we spoke about, right? It is committed, so those sub-operations will have to be undone. They'll have to be redone. Equally so, undo. Not quite, you're building up your transactions, getting ready to write them to disk, and it's not committed, and then that failure happens. Well, then you undo those sub-operations from your journal file. So then we have a composite of these, right? We have a composite of the redo and the undos. And here is an example of one, the hexadecimal 20, right? And this is in this case, initialized file segment. So when you're creating a file, this happens, right? This gets written into the journal file. Alternatively, if you're deleting a file, if you're deallocating a file, it's hexadecimal 02, Microsoft didn't publish these codes. We had to go about, reverse engineering these, right? So it took a bit of time to build up a list of these codes. Attributes, standard file attributes, there are many of, and in NTFS, the primary data structure is MFT. And every file, every folder, every subfolder on NTFS, for example, does have an MFT entry. The MFT entries for those files would have attributes, one of which we're really interested in is the $file_name attribute. And this can hold timestamps, the name of the file, and indeed, if the file is short enough, can contain the contents of that file, in memory, resident in memory. Or else, if it's large, if it's an MPEG file, if it's whatever, an MP3, MP4, it'll store the location or the run of clusters how to access the file, where it's actually located on disk. On the left-hand side, right? So let's just talk about the kind of the input-output processing in the context of application execution, right? On the left-hand side, you see the three main areas. So if you write your code, if you write an application in whatever, Python, Scala, Java, right? You know, you'll write your code to open or create a file. That will call the Windows API in Windows, which will in turn call the native API. And now we're still on user mode, we're still on user level, right? Then that will get transitioned into kernel level, kernel area, right? And we have a lot of things in kernel area, right? We have system services in particular, and there's a lot of system services down there. Again, in this particular scenario, we're interested in two. That would be the input-output manager and the object manager, right? If you look on the right-hand side, it's kind of the same thing, but a bit more detailed. So you're creating a file, you're opening a file, this gets called in the Windows API, down to the native API, transitions across into the kernel level. The input-output manager sends out a request to the object manager. A file handle is returned from the object manager, right? And then it goes back up the stack. That method, the singular piece of communication is that what's written in blue at the very end on the right-hand diagram, the IRP, the input-output request packet, right? So we're going to look at the input, the flow of the IRPs in this encryption process, right? And what does it mean? And what we can get out of it, rather. Oh, that's a bit grainy, sorry about that, apologies. But the diagram on the left-hand side is essentially the flow of IRPs during this encryption, this file encryption process. We're talking file encryption here, not disk encryption. That's a different animal. Don't go near me on that, right? We're talking about file encryption. So if you just think of the main artifacts we're dealing with, plain text file that we want to encrypt. So we get a file handle to that plain text file. We read the contents of the plain text file. We write it into a buffer file. Yes, we have a file handle for the buffer file too. The contents gets written in there into the buffer file. Encryption process kicks in, transforms the plain text into ciphertext, renames the buffer file to the ciphertext file that you put in, right? You know, closes the plain text file and then closes the ciphertext file. So this is all characterized by a series of IRPs, right? On the right-hand side is a sequence diagram. Like we did this hundreds and hundreds of times, we automated this, and the right-hand side is the sequence, and indeed itself a signature of the encryption process. You know, plain text file, file handle, ciphertext file, buffer file, you know, closing the ciphertext file. So this is the kind of signature that we've come to understand. And more or less the last entry in our journal file is when the ciphertext file, the created encrypted file, is actually closed, right? So we're going to use that as a pivot point, if you like, right? So we did this a number of times, and we came across we built up a framework systematically, got a framework together, and we automated this. We wrote Java files, and we also wrote a Python parser. And so, I mean, going straight into from that we were able to establish a methodology, you know, to formulate some steps, and then we executed our case study. And the first thing was we got a hard disk drive with the file, with the encrypted file on it. And the first thing we were going to do is just to verify that that encrypted file was indeed created on that hard disk drive, not dropped in or copied in. So you can run your fsutil object ID, send in the query and the name of the file, and you get your BERT volume ID, and you correspond that with what's in the journal file. The two of them match, so we've a match. We can definitively say this file was created on this hard disk drive. Now, bearing in mind, right, we've extracted the journal file, we've read this into memory, and we go to the very end, the last occurrence of that ciphertext file name that we know we can get it. We can get it quite easily because it's available in the file underscore name attribute. So we go to the very end of the journal file and we work backwards. We backtrack, right? It's a constraint satisfaction problem. We use backtracking. So we backtrack. And now we can see that the $file underscore name attribute, this is the name of the file. This is the ciphertext file. So we're going to chain our way backwards in the journal file to see what files have been touched. We can see other files, the buffer files, a buffer file, a temporary file, or a series of buffer files, depending on the size of the file you want to encrypt, right? But either way, we can see this chain, for example, this hexadecimal, this format, BB80, BB77, 1B1, right? This signifies a file has been created, and indeed a temporary file, right? So we can chain our way backwards to see what buffer files were created, what temporary files, you know. We can backtrack. We can also use the file 0 signature, which gets written in for every file in the MFT, right? And indeed the journal file. So we can use that as a kind of a tokenizer and chain our way backwards when we're parsing. So then from this, then we can determine the plain text file that was used and processed to create the ciphertext file. And again, we extract the name of the file from the very same attribute, you know, the $file_name attribute. And we can get our timestamps from that. And again, we can build up a chronological picture to build up timelines for evidence and admissibility. And indeed, you know, chaining our way backwards, we get at the plain text contents as well, you know. So this is a case, I know the string is pretty small, it's pretty short, and it happens to be recorded, you know, in resident memory of the journal file. All right, and that's fine, that's great, but this is for demonstration purposes. If the file, as we said earlier, was large, was an MP4 or something, this would record the locations and the run of clusters, so we could chain our way. We could daisy chain our way through, collecting logical sequence numbers that tells us what's the next address, the next address to go to. And as we do that, then we can reconstruct the plain text file if it's a pretty large file. That's essentially, you know, from a Windows perspective, how digital forensics fits into the world of forensics and indeed forensic services. And you might hear a lot about digital forensics as a service these days. Equally so, let's talk about, you know, the same kind of process in OS X. You know, it's very similar and yet it's different, you know. And you see the main core components of HFS Plus here. They're the 6 main core components, and they exist contiguously on the volume, right? And the two ones we're after are the catalog file and the .journal file, basically, right? And essentially, you know, since I think it was 10.2 or 10.3 in OS X, journaling was turned on by default, and we're at what now, 10.13. You know, Sierra, whatever. So it's been turned on quite a lot. It was available beforehand, but it's turned on by default now since 10.2, 10.3 in OS X. And again, the same story, you know, the catalog file. The catalog file is a B3 data structure. This is how it stores its metadata in OS X. And again, the same drill, you know, what is the journal file? What is the catalog file? It stores metadata information on the metadata changes on the file system. You know, exactly the same as an NTFS. But what happens here is copies of the catalog file get written into the journal file, right? So now we're running with 2 copies, albeit the journal file version of the catalog file can get out of sync, and we can use that to our benefit too. For example, if a file is deleted off a system, it gets removed from catalog file immediately. However, it might be recorded and buffered for some time in the journal file, and from that, if we correlate the two, we can, you know, conclude that the file was deleted off the system. Again, sorry, I should have said this. Now we're looking at it from a digital forensic point of view, right? We're investigating stuff. You know, all we have is an encrypted file, right? So that's the kind of context so we're going to use a lot of kind of inference as well. So we can use that kind of. You might say, oh, well, look, it's a mismatch in synchronization. Well, we can use that to our benefit too, okay? So we look at the catalog file and the journal file. And again, same modus operandi here. You know, we started in NTFS, we were looking at the flow of IRPs up and down between the user mode and kernel mode. In this case, we're looking at VNOPs in OS X. Same drill. We're talking about the plain text file. We're talking about buffer files, temporary files. We're looking at the ciphertext, the created ciphertext. You know, these are the main artifacts that are generating this traffic. So this is the flow of the VNOPs on the left-hand side, and equally so the sequence on the right-hand side. And same thing, when the ciphertext gets created and gets closed, it's the last thing to get updated, right? So I mean, we could we automated this as well. We wrote a Python parser, and we simply read in the journal file into memory, and we read the contents in, and we were able to enumerate the catalog records, which are B3 nodes, in the journal file, and we were able to get the size of that node from one of those core components. It's called the journal file header. We were able to get the size of that node, and so enumerate our way through the journal file according to B3 catalog file nodes. Of those nodes, then, we were able to extract the records, right? Of those records, then, we're able to extract the file records. Of the file records, then, we're able to get at, using the fork information, we're able to get at the location on disk where our plaintext file is, right? And what also gets written into the journal file on OS X is temporary items. And if you're creating an archive, an encrypted archive, a DMG file, or whatever, the name of that gets written in along with the constituent files of that archive. So in this case here, we have no pointer now. In this case, it's the plaintext file, and then the plaintext file is a component of the encrypted file. In this case, that's the archive that we created. So we can use that information to go searching elsewhere in the journal file. And it so happens that the FS events SD UUID also gets written into the journal file. And what this is essentially is that the FS events D is the daemon that does that live updating on spotlights in OS X, right? It does that live updating. And OS X is essentially, or the spotlights is one vast index of your files, your photographs, your apps, whatever is on your system, right? FS events D is the daemon that does that updating and live updating. So we look for, having got the plaintext file name from the temporary items in the journal file, we're also looking for FS events D entries for that plaintext file, and we find it. We find it, and we find a lot of forensic information: the file ID, the name, the folder name, the file name, timestamps, and importantly, the start block of the plaintext file. And then we can get our plaintext. And it's the same thing, the string is small because it's stored residently, but if it's a large file, we can get the sectors, and we can systematically, harvest and reconstruct the plaintext file by chaining our way through the logical sequence number. Same concept as an NTFS, no mystery. So again, now we've seen it from an OS X perspective, the digital forensics, how it fits into the digital forensics, and then digital forensics into forensic science as a whole. It's a service. So, sticking with this theme of forensics, let's talk about forensics in the cloud, right? And, the landscape is different. We know that. The threatscape is different. The evidence artifacts are different. And of course, the origins and the sources of this evidence are different too. And if you look at the kind of at cloud scale then, right? And you look at the emergence of, I suppose, this DFIR, this so-called DFIR, the Digital Forensics Incident Response. And this is the paradigm that kind of comes to our aid, really, because we're not talking about one or two servers in the cloud. We're talking hundreds, potentially thousands of servers that have been provisioned and orchestrated. So you want to do your incident response, you want to do your digital forensics in that kind of automated fashion, You just can't do it manually. You're not at the races, basically, So this is the kind of what we're looking at, at that automated level as well. And in order to do that, you're relying on some sort of an event-driven architecture, and you can collect your events from collected sources of information like log files, and we'll go through that later on as well. And this kind of helps us on our quest on DFIR. And I see some Amazon folks, good old folks from Amazon here in the audience. And this is a fantastic model that Amazon have put out. And this is what they stand and live by. And it's the AWS Shared Responsibility model. So in other words, AWS will give you the cloud. They'll give you the compute power. They'll give you the networking resources. They'll give you the databases. They'll give you that. And they'll secure it. So they're giving you the security of the cloud, right? And then you and me, when we come along and we use AWS as customers, it's responsible on us and incumbent on us to put the security in the cloud on top of that. So we're talking about doing our hardening, our OS hardening, doing our patching, doing our updating, putting in our encryption, data arrest, transmission, etc. And I think it's a lot of scenarios, AWS incident response scenarios, have evolved or come out of this kind of misunderstanding on the user's behalf. Here's some scenarios that I would have seen for good DFIR, and a key compromise, an access key compromise, and this is prevalent. And you create an access key from your IAM returns your access key and your access key ID, right? And it could possibly be that it was mentioned in the previous slide, you're using GitHub, you're a developer, and you push out your AWS S3, access key, your API key into one of your configuration files, and it gets trawled by one of these botnets for bit mining and all this kind of stuff. It happens, and that's one scenario. It can happen by being careless. I've seen it as well. Best practices aren't followed. EC2 instance compromise would be typically, where the user wouldn't be patching and adhering to standards or best practices again with hardening, for example, and suddenly you realize if you're not patching, your system is out of date and it's now vulnerable and it's probably exploitable by one of these dirty cows or whatever. There's privilege escalation going on, there's remote code execution, and you have an EC2 instance compromise. Of course, the one that scares me is the account compromise, like where root credentials are compromised, and that can happen as well. One or two key individuals in the organization are entrusted with the root credentials, and one of them walks out the door, and you've no operational key management system in place, and there you are, you're wide open. So I would look at them as being fires that you can control, Yeah, things are getting hot and heavy in the kitchen here, you want to get moving. And then I think once your AWS account is compromised by kind of poor handling, lack of best practices, it's very hard to kind of recover from that. In particular, if you're hosting somebody else's data on their behalf, if you're earning your license fees by curating somebody else's data, this is a pain point. So, there's some kind of things that you can code and script, to kind of help you along the way to do the security in the cloud on top of that platform that AWS has given us of being security of the cloud, right? You can check for unexpected resources that have been spun up. You can describe your instances, and you can put in you can have a list or an inventory of your known resources and compare it with the output of your described instances. If there's a deviation in that, ring the bells. Bring in DFIR, and from that then as well, you can detect what access keys were used to spin up these unexpected resources. You can list them down. You can render them inactive. You can in parallel spin up new active keys if you want to maintain continuity of services, and then disable or delete that key that was used or compromised. In terms of the instance itself, create a security group to isolate your instance, and from there then you can start adding in rules. You can start adding in rules into your security group. If you want to control ingress traffic into your EC2, for example, and you can just add a rule for SSHing on port 22, you can do the same. That's another format of doing the same command, but a different, you're putting in the name rather than the block ID. Equally so, on instance compromise, you can you can revoke all access, to all protocols and provide the parameter of -1, and this will cover your TCPs, your IDPs, your UDP, ICMP, all these protocols, and then from that, then you can layer on the access that you want on your segregated instance. You can add in port 80 for your egress traffic, And you can modify the instances as you go and drop in new attributes. And the old architecture, the classic, the EC2 classic architecture, you'd have to stop the instance and then reboot the instance. However, now with the VPC architecture, it's okay, you can do it on the fly. And you know, the AWS account scenario where that's compromised, just rather than going in and modifying all the users that you think you have and you don't know precisely, you can go in and drop in a complete no IAM policy on everything. So you're quarantining it, you're containing it to a certain degree, you know, and you can you can tag your evidence, you can create you want to tag it, you know, good old-fashioned, you know, back to first principles, you know, forensics. You can bag and tag your evidence basically, and this is how you go about it. You can save your instance information as well. You can output it to various logs. And this command here, you know, describing your instances, and then you pass in the instance IDs. That can be highly verbose, or verbose is the wrong word. It's highly paginated, but it's good quality information because it gives you information on all of your stuff, your VPC level, you know, down, you know, the type of EC2 instance, your OS, you know, the security groups you're using, your routing table information, you know, your routing, you know, subnet information, your network ACLs and all this. So it's very good forensic information. And again, you know, you're getting ready for your DFIR process, you can create your snapshot. And you have to be cognizant of the fact that your EC2 here has to be backed up with EBS, you know, the block storage, to create your snapshot. And you know, from that then you could load up your favorite forensic distribution and go to work then doing your standard forensics. And you can create a volume then from your snapshot, and you can also create an encrypted volume. And assuming that your EC2 is backed up with EBS that supports encryption. And you know, this for many reasons you could use this, but DFIR is a very good use case scenario. You could describe your volumes in the default region that you're running, you know. There's a sample of some of the tools, top left corners, your endpoint tools, you know, your Mandiants, your end cases. There's GER there as well, Google Rapid Response. You know, they have an open source version of this, and it's a very good, you know, enterprise-wide collection tool. And your network stuff, you know, like Paul previous to this was talking about Wireshark, Moloch, your software-defined write blockers. You can do your memory captures with Lime and FTK, Imager, etc. And there's a whole list of other open source projects that are ongoing there and pretty good. So I think it's prudent as well if you're in the DFIR game to construct and prepare a response workstation. You know, base it off whatever an Amazon machine image, an AMI, and you know, put in your operation, whatever you configure your operation system, your OS, your flavors, the various tools, your favorite distributions that you want to use. You know, and you could liken it to, you know, you're preparing and initializing your robot for war, right? And you know, you can have a dashboard as well that talks to your AWS regions, you know, and lists off the various recently launched resources that we spoke about earlier. And it'll list off your various types of AMIs, etc. And you know, you can do your analysis then, you know, you can do your memory forensics or your disk forensics. And the disk forensics, you know, you have those artifacts that get written to disk, you know, the remnants, the leftovers of what malware, you know, it gets written to disk. And this helps us a lot. This helps us build up evidence and a picture of, and the modus operandi and the objective of the attacker. Equally so though, memory forensics too, albeit the artifacts aren't written, you know, they're more volatile, etc. So there you are. You have a little robot ready to go to do your DFIR battles for you. And I would, you know, it'd be prudent as well to be forensically ready. You know, assume that your environment that you're operating in is going to be at some stage, you know, a crime scene, right? There's no shame in that. It's just preparation. So you're forensically ready, and you could build up your evidence environment. You can build up your own evidence ecosystem with your little bot army at the center of it, you know. And you can go and you can collect evidence from VPC flow logs, you know, your VPC over on the left-hand side here, and that's your virtual private cloud. And this kind of contains all your resources. And the VPC flow log is essentially that net flow information that gives you information on the traffic flowing into your VPC, out of your VPC, and indeed within the VPC itself. And you know, so that's really good kind of forensic information there. You could also use CloudTrail and AWS CloudTrail, and this kind of gives you the account, the big picture on the account, you know, and what APIs are calling each other, and you can see the flows there. And you know, from an operational point of view and a compliance and indeed a governance perspective, you know, it's invaluable. You know, CloudWatch, CloudTrail. Sorry, that was CloudTrail. CloudWatch is very much in relation to the usage, what you're using, and if you need to put your cap on your resources, you can set alarms. And indeed, it's useful as well for incident response, because if you're one of those people that doesn't use EC2, just uses AWS 3 for backup, you know, and AWS CDN for pushing content to your website, and you don't use EC2, you can put an alarm in. Put an alarm in for one EC2 and over. And you know in your heart and soul, if you get an alarm for one EC2 and you're not using it, something's wrong. You know something's adrift, right? And that can happen. We just spoke earlier about our access key IDs our secret access keys being compromised. You know, these are alarms that you can put in. The AWS config as well helps you kind of baseline, and if you're doing hardening on your OS, if you're whatever your security groups and your configuration that you have in terms of you standardize your CloudFormation templates, and any deviation from those prescribed standard settings, you can get an alarm and generate your alarm. And folks, that's about it now. You know, thanks very much for listening. I think that's the end of it. Yeah, thank you. Thanks very much.